Welcome in. So derivatives of power and radical functions. So this is kind of the beginning of recognizing patterns, okay, when you are going to be taking derivatives. Now, what is a derivative once again? Well, a derivative is nothing else but simply a function. So please remember that. It is a function. And that function just tells us what the slope is at every single point that is defined for that particular derivative, right? So we can find out exactly what the slope is at any point on the function as long as it's defined. And it was defined from first principles, as you studied kind of the beginning in calculus, as what I just highlighted there on the screen. So it's the limit as h approaches to 0. You know, the function, you substitute x plus h into it, and then you subtract fx. Okay, so the x is the actual variable that we have, and then we're going to be trying to find what the slope is. Now, we utilize different notations, of course. Okay, so this one or this one. I most of the time will stick to this one because it's shorter and easier to write. And what I will want to be able to do is I want to be able to find the actual slope, okay, or the derivative at every single point where it's defined of all of these wonderful functions that I have for you. Now, you might say, wow, well, that's quite a lot. Are you going to be doing this all the way from these first principles, utilizing our limit definition? So it does indeed come from this, but we don't really need it. Okay, and in order to prove it, okay, I will show you, and I'll put up links for those who are interested, especially anyone who's going into mathematics or going into, for example, engineering. So engineers, you may want to look at the actual proofs of how to find these, so you just kind of get a gist of that. But for anybody who really just wants to know what the derivative is, you'll see that the actual pattern that comes out for all of these is actually pretty simple, okay? So let's dive in here. Now, I'm going to start with the first one, and let's not forget what we're trying to actually do with these functions. We're trying to find the slope. So do I always need, you know, this particular item to be able to solve this for the actual derivatives? Well, if you're thinking about a function like this one, which is nothing else, this c stands for a constant, so it's just some number that we have. Doesn't matter what number it is, okay? Now, if it's a particular number, then what it is telling us, if we wanted to find the slope, then this is just a constant, right? So this function is a constant, which is nothing else but a flat line. So if I would be graphing this out within here, so I would just get, so here's my x and then my y, and then maybe this constant doesn't matter if it's positive, negative, or 0, so it would be just flatlined in here, and it would just continue to the left and to the right, okay, whatever this c might be. Now, it's easy for you to tell that, well, wait a minute, this has a slope of 0, right? It's just a flat line. And that's not surprising that it turns out that the actual derivative for any point, okay, that is of a function which is a constant, is simply 0, because the slope is 0 at every single point. Now, can you find this answer by substituting into this limit? Yes, you definitely can. You can find the limit both from the left-hand side, the right-hand side if necessary, and then you can find out what it is. But it's actually not that hard, because what you're going to get is, okay, if you substitute this back in here, what you're going to find is you're going to get this term. If you substitute x plus h, well, there's no x to substitute, it's just simply c. And then the second one, which is this one, which is minus c. Okay, so that's what I have. So my numerator is just simply equal to 0. My denominator is equal to h. Now, you might say, well, wait a minute, I have 0 over h, and h tends towards 0. That is true, indeed, it tends towards 0, but it's never actually 0, right? It just goes to 0 from the left and to the right. But it's always some number, either both positive and negative. So if h is actually just some number which is very tiny, no matter what we choose, this whole thing just simply means 0 over h, which is 0, which is exactly, okay, what we get over here. And here is the intuition behind it, because it's simply just a constant. Now, I'm not going to be explaining this for every single function that we have here. Okay? I'm going to show you what all the derivatives actually are. And some of them I'll explain just so that you get a gist of what we're actually doing. And then the others, I'll point out those links as I've mentioned. So that's the slope of my constant. So anytime I have a constant, my derivative of a constant is simply equal to 0. So now moving forward, instead of putting it into this, okay, you can just right away say, well, the derivative is 0. Now, what about the second one that we have here? Okay, what about this one? Well, again, so think about what this is. This is nothing else but simply a line which passes through the origin, right, with a slope of 1, right? This is nothing else but simply a line, okay, that will just simply pass through our origin, okay, that we have. So if this is my origin right here, it's my x and my y. So this is my line. This is nothing else but simply y is equal to x. Well, what is the slope at every single point? Well, we know what the slope is. The slope is always equal to 1. So within here, again, sure, I can certainly substitute it back into this right here and then find out what the actual slope is. But I can also think about the intuition that it's nothing else but just a line. And what I will find is that this is simply that the derivative of this one, okay, is simply equal to 1. It is actually the slope, okay, which is right in front of it, okay, that we see there. So that's my second one. Now, what about the rest, okay? What about if it was x squared? So now we're getting into these power functions, right? So we're getting into these power functions, and then here we're going to be assuming that n, okay, so this variable that I'm putting into all of these is going to be some natural number. So 1, 2, 3, etc. Okay, so that's what it will be. However, we already have identified, okay, what x and the derivative for x is. It's just 1. Now, the derivative for x squared turns out to be equal to, okay, the exponent right here, which is brought down to the front, and then this is going to be just the variable x. Now you might say, where does that come from, right? How do I know that? Well, I know it because if I did substitute it back into here, then that's exactly what I would find. Now, bear with me, okay, for just a moment, because I want to show you that in general, what happens. I'm going to just remove this just so that I have space. In general, if this x is to some power n, so that exponent is maybe 2, maybe 3, maybe 4, maybe 5, maybe 6, doesn't matter, maybe 100. Turns out that the derivative is always equal to the exponent multiplied by your variable. And now what you're going to do is you're going to subtract 1 from that exponent. So that's what that would be. So for instance, if I had x to the 5, then my derivative would become 5x. 5 minus 1 is 4, and that is actually my derivative. Now you might say, well, that's shocking. How does he know that? Again, it does indeed come from here. And if you are interested in that derivation of seeing why that's the case, then I'm going to put up a link up above to the entire proof. But for most students, what they'll do is they will simply just memorize that that is the derivative of a power function. Now, you might then ask, well, I mean, what would happen if I started to have, as you can see there below, what if it was negative? What if instead, this was negative 5? What would be the actual derivative? Well, it turns out that it still follows exactly the same thing. So if you have a function and it turns out that it's, let's say, 1 over x to the power of n, let's not forget that it is equal to x to the negative n. That's just by exponent, right? Rules that we have. And once you put it in that form, the actual derivative is equal to the exponent, which is now in this case is negative n, to the variable x, and you will subtract 1 from the exponent. So it follows the same pattern, which means that if I had something like this and I wanted to find the derivative, so the function for all the slopes, this would just simply be negative 5. X, negative 5 minus 1 would give me negative 6. And this, of course, can be written out in this form, x to the 6, like that. And that's exactly what it is. So that link that I just showed you also talks about the negative case and then derives it for you. So that's pretty cool. Now, what happens, okay, if we continue in here, because it seems that the pattern is we take the exponent, we bring it to the front, and then we subtract 1. Notice what would happen in here if I go back, okay, for instance, to this one. Well, how did I get this? My n was equal to 2. I brought it down, which was 2. I subtracted 1 from the exponent, which means that it's just 1, except we don't really write the 1 in there, but that indeed is the case. So that's what happens in here. Now, you can also do that with this. Now, the exponent here is x to the 1, so we would bring 1 to the front. We would have x, and then it's the exponent minus 1, which is 1 minus 1, which would give us x to the 0. But x to the 0 is always 1, and that's why you have your derivative. So the derivative has a pattern, and then now you might say, well, that's interesting. Does that mean that all of these follow the same pattern? Meaning, what if I have now some number in front right here? Do I still do the same thing? Yes. So a constant, so a number in front, so a factor, which is just a number, will not change what we do. All we're going to be doing is we're going to be taking, okay, this, which is just highlighted above there. Now, we know what the derivative of that is. So it's going to be n, x, n minus 1. And that c will just simply stay in front because it is a constant. So that does not change anything for us. Now, how come the c, how come the constant just remains there and we don't do anything with it? Well, that comes from the fact that if you substituted back into our original right here, then what you would have in here is, let me just copy this. I'm going to kind of take this out. I'm going to substitute an extra page in here just to show you that there is no worry about a constant in here, because what you're going to get is substituting this into there. So you would have gotten c, and then you would get x plus h to the, now this is n minus c x to the n all over h, like so. However, notice that my c is just a constant, which I can factor out completely, and I can factor it out outside of my limit. So now I would get this as h approaches to 0. And of course, this would be x plus h to the n minus x to the n all over h. And this is just the derivative of the power function with c being multiplied right in front. And that's exactly what we got over here. So we don't touch the constant. So that's pretty cool. Now, what happens in the case where we start dealing with radicals? Does this change in any way? So here is my first. So this is the square root of x, right? So this function isn't the nicest. It also, please remember, is not defined, right, for negative values of x here. So we always have to be careful where this function is defined. Now that would also be the case, for instance, above. If we did have this in the denominator, we, for instance, can't have a derivative at 0 within here because the function wasn't defined at 0. So that's something we also have to keep in mind, okay, as we're going along. Now, coming back to these radicals. So the radicals are actually exactly the same because if you remember from grade 9, when you do study radicals, they can be changed to fractional exponents. So these are equivalent, right? So these are exactly the same. So these are equal to each other, just written in a different way. Now, we like to write the radical itself, the symbol, but in the fractional case, please remember that there is actually a 2 in here, and that's what happens. Now, finding the derivative of this is actually the same. So the rule for these radicals is that you take your exponent, you bring it in front, and then you subtract 1 from it. Now, of course, I can find out what that is. 1/2 minus 1 is negative 1/2. So therefore, this would have been just simply 1 over 2. And then this would have been my x to the negative 1/2, which I can bring it back now back to actual radical symbol. And in that case, this would have been 1 all over 2. And then this would have been the square root of x by using the exponent rules. Now, if you've forgotten radicals and the exponent rules, I'll put up a link up above there for you, okay? In case you wanted to review that kind of material from grade 9, possibly for some of you, maybe from grade 10. Now, does this hold true, okay, as I'm going along? So within here, do these derivatives hold true for the rest of them? So what if I had this? Well, this is equal to x to the power of 1 over 3. And now finding the derivative of this, so the derivative of this one right there, is nothing else, again, by taking the exponent, putting it in front, and then subtracting 1 from the 1 over 3, which would have been negative 2 over 3. And that is the answer. So, what happens in the general case? Now, I write here an m, right? So m is, for instance, some natural number. It's not equal to 1 because we can't really take the square root of 1. Okay, or sorry, the first root of 1, it's just then x on its own. So I'm going to assume that it's either, squared, cubed, to the 4th, to the 5th, 6th, etc. So in those cases, the general case for these turns out to be that this is nothing else but x 1 over m, and taking the derivative of this is equal to 1 over m, goes in front, and then you subtract from the 1 over m minus 1. So that is the pattern that you will notice for all exponents. Now, for anybody who wants to now see the proof of the radicals, so if you want to see the proof of this whole thing and how that exponent actually is carried through and what the derivative is, I've done a proof for that, and I'll put up a link up above there for those who are interested. Again, those going into math, those going into engineering, kind of engineering science or anything related, kind of harder, university level programs that heavily rely on this. It's good to know how to do these proofs. So you may want to take a look at that. For others, you hopefully will notice a pattern recognition in here. So if you continue this, now I have done many of them. What happens if you have something like this. Now you can say, well, wait a minute. What does this actually mean? Well, so what this actually means is that I have 1 all over. Now this is just x, 1 over m, which is, again, simply because it's in the denominator, I can bring it up by exponent rules to the numerator. So this is going to be x to the negative 1 over m. What's the derivative of that? Well, the derivative of this becomes negative 1 over m multiplied by x, negative 1 over m minus 1. So I think by now you're recognizing the pattern. So these are always continuously the same. So for instance, if I had something like this and I wanted to find out what the derivative is, I would go like this. Well, this just simply equals x to the negative 1 over 4. So now finding the derivative by using my rules, this is negative 1 over 4. And then I'll find x, negative 1 over 4, minus, the 1. And I have my answer. Now, of course, you can still simplify this. So what is this equal to? Well, negative 1 over 4. Finding a common denominator, so within here, so that's what that would be. This is negative 5 over 4. And that's what that exponent would be right there. All right? So that's the derivative. And now you have to be comfortable with going between radicals and then jumping into fractional exponents. So that's something which is useful. So those are the derivatives in here. Now, how about, so if I would continue this and generalize it to this case, what is this equal to? Well, what is this equal to? This is x to the n over m. So now it's the general power function where you have a rational exponent. Now, we're going to assume that it's in lowest terms, that fraction. So we can make that assumption, but it doesn't have to be. The derivative of this is always going to be simply the actual exponent multiplied by the variable, and you're going to take n minus m and subtract 1. That is the general case for these. And for all of them, so I'm going to leave this in here, up above there. If you would look at this one, this is simply x. Now it's going to be, because it's in the denominator, so if you simplify this, it's going to be negative n over m. And all that changes if you wanted to find the derivative of that. So it's going to be negative n over m times x minus n over m minus 1. That's for that. Now, for anyone interested in proving, these cases, so these particular cases that you have here, and showing that indeed it's the same as all the others, I'll put up a link up above there for you, for that particular proof. That is now as hard as that gets, in terms of proving it. It is a little bit lengthy, that video. However, it's worth your time, if you're interested in where does this come from, because all I'm using is the standard definition of the limit, substituting everything in, and then going through a lot of different little tricks to get to this final result, which now we have a pretty nice pattern recognition. Now, what happens if you have a constant in front? Does that change? No. So all that will happen, like the previous case, this c, will simply, if you took the derivative, it will still be c. And then you want to know what the derivative of this is. Well, the derivative of that, we have just, told you that this is what that is. I'm going to just copy it, paste it in, and that's what it would be. So this is just simply saying, if there is a constant, it just simply stays there. It doesn't disappear. Now, you might think, well, that's different because from the original case, when we had a constant only within here, didn't we say that it was 0? Yes, but it had nothing else beside it, right? It was just a constant. It was just a flat line in terms of a function. Here, putting a constant in front, okay, this doesn't mean that this is a flat line, right? So this, okay, is actually multiplying an actual power function that we have. So if I took all of these, and summarized it, the summary is you take your exponent, you bring it to the front, and then you subtract 1 from the exponent to get whatever your derivative will be. Okay, so now to finish this video with a few examples, so here's some functions that I have for you. So if you were doing this and I asked you, all right, so what is the derivative? Well, the derivative, the constant stays in front. Okay, now the 7 will drop to the front. So this is going to be 3 multiplied by 7. X, 7 minus 1 is 6. So the derivative is 21 x to the 6. And that is pretty cool, right? To do it so quickly and not utilizing the actual limits. And so what I would want to do is I would want to take this actual function and show you that indeed, okay, this is the case. We're finding, remember that the derivative is the slope at every point where it's defined. So if I take decimals and I load it up in here, okay, so I'm going to take decimals. I want to just show you. I'll do it for one example. So here is the function, right? Fx is equal to 3x to the 7. So this is what it looks like. It doesn't look the nicest, okay, but that's what it is. Now, let's put in, okay, we want to find a slope at any point. What we're saying is we're saying that the actual slope, okay, or sorry, the derivative is g, okay, x is equal to, we said 21x, okay, to the 6. So that's actually the slope function, the derivative function. That's how it looks like. Now I'm going to unhighlight it and I'm going to put in here, okay, because what I want to show you is at any point. So now let's pick an x. It doesn't matter what it could be. So let's say my x, okay, I'm going to call it, let's say a is going to be equal to 1. Let's, make it there between, let's say, -1 and 1. So I'm going to be spanning from -1 and 1, right? Now, I know what the actual, so the point itself, okay, I can plot. So that's going to be a, for instance, right here, okay, and I'm going to be substituting that a inside there. So here you can see it there. Now, and I can move this point now, right? So I can move the point along. I want to be able to see, okay, the slope, and I'm going to find the tangent line at that slope if it really is, okay, this 21x to the 6. And if I were to do that in here, so if I want to find, well, I know what the point is, right? If I have a point and I have a slope, so my slope m is equal to actually g at a. So that is my slope, right? That I have. Now, if I want to find the tangent line, which is y is equal to mx plus b, I can certainly do that. So in order to find, so please remember, okay, this is, something nice. This is going to be my slope at any point, right? Now, a line, a tangent line is y is equal to mx plus b. So I know what x is, so that's a, right? I know what my slope is, and I certainly do know what my y is. So my slope within here, the way that I did it, so that's my m, my x, okay, if I substituted, that's a. My y is going to be g at a, right? That's the actual point itself. So I can solve for this b. My b is equal to g at a minus ma. And that's going to give me the y-intercept. So this is going to be, let me put it in here, b is equal to, okay, g at a minus ma, Okay, so this is now my y-intercept. And I can now plot, so y is equal to mx plus b. All right, so now this is the actual point that I have in here. Okay, so that's my actual line. And now let me see, just to make sure that everything is lined up in here. So GA, this should be FA. This is F at A, okay, and there you go. So within here, so this, I made a mistake there. So this is not GA because we're not finding it at the slope, we're finding it at the line, at the actual function. So that's FA. And notice, now on the right-hand side on decimals, indeed I have my tangent line, and now this is the actual slope, the tangent at any point I like. That's what the derivative is, right? The derivative is the slope. And if I have the slope at any point, I can find my y-intercept and I can now draw this actual, right here, the tangent at any point for any function that I like. So that's pretty neat that I can do something like that. Now, that is for you, okay, in order to, you can try it as well and then hopefully get intuition, what are we actually doing in here? That's what the derivative is. Now, the derivative is a function which gives us the slope at any point. That's kind of the idea. Now, what about kind of the rest in here? Let me remove this from here. So that was my first one. What about now my second one? So this one, I would say, well, I can rewrite this. This is -2, x to the -4, right? And now, if I want to find the derivative, well, that is the constant. So the constant is -2. So this stays in there. And now this right here, so I will multiply it by -4. I bring down the exponent times my x, and then -4 minus 1 is going to be -5. So this is going to be 8x to the -5, which is now my actual derivative of that. And because I enjoy, this so much, what if I now change this? So notice in decimals, what I'm going to do is I'm going to say, now my function is -2 over x to the 4. So it looks pretty funky there. Okay, so I'll do that. I'll zoom out in just a moment. My derivative that I found was 8x to the -5. All right, and now let me do that. And there you go. That's all that I had to change. The rest is the same. You plot a point, you find what the slope is at that point, and then you find the y-intercept. And now notice, I can basically go anywhere I like, right? So I can do anything that I want. So within here. So notice if I go over on the other side, I can do that as well. That is really cool exercise, for anyone who would want to be able to see, and try this out on their own. So you can now visualize the actual tangent lines and finding from the slope. So I won't do that for the rest in here. So it's a little bit too much excitement for me. However, if I delete this, now I can find the rest of the derivative. So what about this one? So this one is, I'm going to simplify this. So -x, in the denominator, notice this is x to the 1/3. So within here, because I have an x and an x, so this is the exponent rule. So this is nothing else but -x, 1 minus 1/3, right? So these are just the exponents. So that's subtraction. So that is equal to -x minus that, which is going to be 2/3. And now if I want to find the derivative of this, well, the derivative is that negative just simply means it's -1. So this is going to be -1 times, bring down the exponent. So that's what that would be. And then x, 2/3 minus 1. So my final, so this is -2/3 x, and then if you subtract the 1, this is going to be -1/3. And that is my derivative. okay, at all the points that it's actually defined. Now, we can't really put 0 in there, so that definitely won't work because the function is not defined here at 0. And it's also, okay, something that we have to take into consideration for the derivatives, okay, when we are finding these things out. So here's a last one. So this one looks brutal right here. However, so notice what this will be. This is 4, right? Inside of that bracket, that's just x1 over 3. So that's what this is. This is to the 5. Now I can bring this inside here. So this is 4x 5 over 3. And now finding the derivative of this, no problem. 4 times my exponent, 5 over 3, x, and 5 over 3 minus 1. And then you can find out what that is. You can simplify it, and you get your answer. All right, so a pretty lengthy introduction to these derivatives, but I hope that it gives you a good sense and understanding, okay, of what the derivative is of a power function and all these radical functions. In fact, radical functions are just power functions. We just have to be careful where they're defined, and then how do we find that derivative. Okay, thanks for watching. We'll see you in a future video. Bye, everybody.